Once started up, the Pi receives the sensor data from the Arduino via Bluetooth and uploads it to an S3 bucket at the back end. Then, the scanner identifies the scanning bounds by running the motors until micro lever switches are pressed at the end of each axis. Next, the machine needs to understand where it is relative to the plant bed. Computer vision locates the corner of the bed marked out with blue tape. The position of the scanner can then be fine-tuned using serial communication between the Pi and the motor Arduino. The machine now knows where each plant pot is and is ready to measure its height. To measure the height of the plant, the scanner arm moves down until the infrared proximity sensor fixed to the end of the arm detects the presence of the plant. Computer vision is also used to determine the plant's surface area. Frames are filtered in order to isolate only green contours. The area of the contour closest to the center of the frame is converted from pixels squared to millimeters squared. In order to maintain accuracy with poorer lighting, a normalization function was created which modifies the image pre-filtering by maximizing the range of pixel values whilst maintaining their RGB ratio, thus creating an image concerned only with color and not shade. The area and height data are then sent to the backend's S3 bucket. Finally, photos are taken from the top-down, left side, top side, and right side of the plant before being uploaded to the S3 bucket. The system can be triggered to begin the scanning process at set times in the day using the Pi's crontab scheduling tool, which runs a shell script in order to move into the correct directory and virtual environment before calling the main Python script.
We placed a total dissolved solids probe to estimate electrical conductivity, a pH probe, and a temperature probe in the hydroponic solution. These three probes are connected to an Arduino. On top of the Arduino housing is a light intensity sensor and a BME 280, which measures air temperature, barometric pressure, and humidity. When the Raspberry Pi sends a read request, the Arduino takes a reading of all the sensors and sends it to the Pi via the HC05 Bluetooth module. Once the Pi has received the readings, it formats them into a CSV file and uploads it to the S3 bucket.
The sensor data received is saved into a CSV file, which is then uploaded directly into the S3 bucket. The same protocol is followed for the plant height data. After the image of the plant has been taken, it is uploaded directly into the S3 bucket using Boto3. After a batch of images have been uploaded, a message is sent via MQTT protocol to the AWS IoT call. Once the message has been published to IoT call, an SNS message is triggered.
Now we move on to the machine learning part of the workflow. A Lambda function waits for the SNS message before feeding the images into an image classification model in a batch transform job request. The status of the batch transform job can be monitored in this tab. The images are processed by the model, which returns the status of each plant with its confidence rating. After a few minutes, the job is complete. The inferences of the model are placed in a separate S3 folder.
Generated SageMaker data must now be appended to an SQL database, allowing for further querying. This is done using a Lambda function, triggered from a CloudWatch event once SageMaker has finished processing. This Lambda function uses an SQL query to append the new JSON data to the existing database. This allows all these probabilities generated using image recognition into the database. Furthermore, there's sensor and height data which is already structured. On upload, this triggers another Lambda function appending this data to the existing database. This database is then queried using SQL using Amazon QuickSight, allowing for live insights into the data. First, it allows us to track the height of our plants and their growth behavior over a custom time range, as well as plant sicknesses, allowing for interception by the farmer. On the other hand, the environment monitor tracks variables of the environment compared to past data, allowing for growth patterns to be revealed, as well as certain goals to be set that are based on research, allowing for the user to create the perfect environment for their plants